For our next video, you're going to need the copy of the light blue piece of paper and the purple piece of paper. We're going to look at how to read a distance versus time graph. We're going to start with the blue one. No matter what the numbers are on the graph, you know, how many meters or kilometers or seconds or minutes or hours, whether we're talking about a person walking, a car driving, when a distance time graph is used, when we see certain lines or certain features, that means the same thing no matter what object we're looking at. So we're going to go over some of the common things. That way we can be able to read a distance time graph. Now, you did create both a position time graph and a distance time graph in the last video. Here we're going to look at, if we weren't creating it, if we were given the distance time graph, how would we know what the object is doing? So in this case, if we look at the top one, okay, we always have distance on the y-axis, time on the x-axis. If we see a flat, straight line, like horizontal, okay, that means that time is passing, okay, no matter what these numbers are. It could be 0, 1, 2, 3, 4, 5, or it could be 10, 20, 30, 40, 50. Time is passing, but the distance is not changing. If that's 20 meters, that object is not going anywhere past the 20-meter mark in that time frame. So there's quite a few ways that we could describe the motion of this object. We could say that there is no motion. Okay. Other ways, we could say that it is not moving. Okay, that's really what no motion means. So we're going to write not moving. Another way to describe it is stopped. So anytime if you were reading a story and it said that the bus was stopped at the bus stop for 30 seconds, you know you should see a flat line on that graph for 30 seconds. Some other words that we might see: at rest, okay, that means the same thing as no motion, or the word stationary. Okay, think about a stationary bike. That's like an exercise bike where you're pedaling and pedaling, it's not going anywhere. Station means it's not moving. So anytime that we see this line on a distance time graph, we know that that object is not moving or that object is stopped. Okay? Anytime that we see a line that's at a diagonal, so it's still a straight line, but it's not horizontal anymore, it's more diagonal, this is something that means constant speed. So we're going to write constant speed. Again, the key word there is constant. So in this case, another way to say that would be steady or same. If the speed is not changing, if the speed is staying the same, the object we describe as moving at a constant speed, and the line looks like this. Now, if you look at the graph just to the right of that, and you see two different lines, we see a dotted line and we see a solid line. They're both still straight lines that are diagonal, so we're still talking about constant speed. Okay, we still have that word constant, meaning the same or steady, but we can actually tell, just based on the line, which object was moving faster. So say this was car A and this was car B, and we were tracking both of their distance over a certain amount of time. The steeper the slope, okay, or the more up and down the line, the faster the object is moving. So this car, car A with the dotted line, was moving faster than this car, car B, with the solid line. Another way to think about that is if we measure, say we picked one point, like right here, and that was the distance, like the ending point for that first line. At this time, who traveled a farther distance? Well, this car did, right? Because this one, say, only made it 20 meters, and this one went 40 meters. If you can travel farther in the same amount of time, you're considered faster. Think about your mile time. In PE or pre-athletics, if you're all running the mile, the people who finish first would be described as finishing faster than the people who finished after that. or in this case, in a given amount of time, if you can travel farther than this person, then you're going faster. Another way to think about that, if the flat line is when an object is not moving, this would be going a little bit faster than that, a little bit faster, and then the more slanted your line is, or the steeper the slope, the faster the object is going. Now, sometimes, I'm going to move down a little bit, sometimes we might see graphs, distance time graphs that don't have straight lines. So that means that we are not moving at a constant speed. Okay, we are still moving because it's not a flat straight line, but now we're moving at what we would call acceleration or deceleration. Acceleration is the one on the left. And in our notes, when we talked about acceleration, it could be technically speeding up, slowing down, or changing directions. Many times when we talk about acceleration, that means that the object is getting faster. If you think about a car, you have two pedals. There's a brake pedal and there's the accelerator. Well, that's what you push. That's like the gas pedal. That's what you push to accelerate or to speed up. So acceleration means speeding up. Or you could also say gaining speed. Or you could even say getting faster. Okay, so it's starting at like 0, 0, and think about a car. If you were sitting at a stop sign or a stop light and then it turned green, you would accelerate. Okay, remember, the more slanted up and down the line, the faster it's going. So you start out not as fast, but your speed is increasing to get faster. The opposite of that, say you were in a car and you were approaching a stoplight, you would be slowing down. You're starting going faster, okay, more up and down on your line, and then as it gets flatter, that means that it's getting slower. The scientific term for this, or a more specific term, is deceleration. Slowing down is another way to describe that. Or instead of gaining speed, we could say losing speed. Okay. This is going to be a good page to refer back to when you're doing some activities in the future, or when you're looking at a distance time graph trying to read it. Remember, it doesn't matter what the numbers are or what object that you're graphing. You can always know that the flat line always means the same thing. It means no motion. Or the straight line always means constant speed. Curved up is acceleration. Curved the other way, deceleration. Okay. So if we do some practice, I'm actually going to do the bottom half of the purple page first, because this is our distance versus time graph. So if I wanted to know what's happening in section A, and actually, if you got one of the purple papers where these words got cut off, that should say distance. Okay, the bottom one is distance, the top one is position, but I want to talk about distance first, because that's what we just talked about right here. Okay. So if we look at segment A, section A, where it's curving up, I want to look over here. Which line is that similar to? Well, that's similar to the acceleration line. So I know that in that section, whatever time that might be, whatever distance that might be, the car is speeding up, or whatever object it is. So I'm going to say that is acceleration. In section B, from here to here, now I see a straight line, so I know that that's going to be a constant speed. So I'm going to write constant. Section C is flat. The distance is not changing. Whatever that value is, that's what it is at the start of section C, and that's what it is at the end of section C. So that's what we call no motion. Remember, other ways to describe no motion would be not moving or stopped, at rest. In section D, it's again a straight diagonal line, so that is going to be constant. Now remember, where there's two straight diagonal lines, I can compare, and whichever one is more steep, more up and down, and less flat, that's going to be a faster speed. So in this case, B compared to D, B is more up and down, more slanted, so I can say that B is faster than section D. This would be a slower section. Now, most of the time when we look at graphs, we are looking at distance versus time graphs. Like we said in the last video, speed versus time are some graphs that you'll look at more in 8th grade. We'll talk a little bit about position versus time here in 6th grade, but most of our focus is on distance versus time. I do want to look at, though, the position versus time right here, just because there's one piece that's going to be a little bit different. Okay, so in a position versus time graph, this is still considered a constant. Okay, more importantly, though, it's moving away from the start, because remember, this is our starting point, and whatever our highest point is, that's like our ending point. So from A, we know that it's moving away from the start, whatever that starting point may be. In our example in the last video, it was from the science classroom to the bathroom. Section B is exactly like what a flat line is on a distance time graph. When position is not changing, distance is not changing. That means that there's no movement or no motion. Now those backward lines, remember, that is where a position versus time graph is different, because now it's going back toward start. It didn't quite make it all the way back to the starting line, but it went back towards the start. Now it's going again back away. Okay, so away from start. And in this case, it's a lot more of a flat line, so we know that it's going slower than it was before. It's taking it a longer time to go an even shorter distance. Okay, these are going to be good reference pages when we start looking at reading distance versus time graphs. Again, keep in mind that the only time we'd have the going away from start is, and then coming back to start, is in a position versus time graph. These are going to go in your journal on pages 8 and 9. Okay. You can title them both reading a distance v time graph. Remember, that stands for distance versus time, and they can get glued in just like that.